First time.
Right. Good afternoon, everyone. Again, I'll apologise in advance for my English. I have made the point I am Northern, therefore I probably have a bit of an accent. Could be tricky to understand. A little bit less sort of technical in terms of showing off LabVIEW capability from me, because I only really started using LabVIEW about a year ago. It's more sort of talk about what we are, what we do, and some of the ways in which we started to integrate LabVIEW into our particular business. So here's the next screen, that one. So I'll talk to you a bit about CPI as a company for those that who might never have heard of us. Sort of scale it in a little bit to the Formulation business unit, which I'm part of. Talk about my role and the capability we have, and then sort of spend the second half of the presentation talking about how we started to use LabVIEW and some of the ways in which I'm quite keen to continue and begin using it in the future. So CPI, it's not really fair to say we're a not-for-profit agency. We're a not-for-our-own-profit agency in that we work with a lot of other companies to help them to achieve profit and to innovate their processes, commercialize new things. We are part of the UK government's high value manufacturing catapult, and of all those particular other groups within the high value manufacturing catapult, we're the only one who's based more in chemistry rather than engineering. So speaking for myself, I'm a chemist by trade. We work with a few chemical engineers here, but I don't claim to be any particular knowledge in that regard. So we have a lot of different business units. We work across basically wherever there seems to be a gap and an opportunity for us to sort of help. That's usually where you can find us. We tend to be more about bringing people together rather than having a lot of fancy, clever technology. But to be fair, we do have some pretty nice kit, and I will introduce you to some of them later on in the presentation. So some of the business units we have biotechnology. We have a growing area in biotherapeutics, which has become particularly prevalent with the way the last year has gone. Formulation materials, which is my particular area of interest. And we've also got printed and flexible electronics and photonics center, also based in the same area. And this is all tied together with quite a strong and improving digital infrastructure. So in terms of where we're at, so we're fairly predominantly based in the northeast of England. So the Wilton Centre was our sort of founding office, sort of grew out of the old ICI, which there may be a few people around that remember that. Wilton is now currently home for our biotechnology capability. Addition to that, we've got the Darlington facility, which is where a lot of our biotherapeutics work goes on. Sedgefield is the particular area that I'm involved in. So we have quite a large campus here where we have our printable electronics and formulation. Newton Aycliffe, we have sort of a site there for scaling up a lot of the electronics and flexible electronics that we develop at Sedgefield. And we're pleased to sort of add Glasgow to the family now with the new Medicines Manufacturing Innovation Centre, which is a sort of collaboration between ourselves and a lot of industry-leading pharma companies to sort of really push the boundaries of modern medicine technologies. So in terms of formulation, as I say, that's where I'm from, CPI Sedgefield. That's a lovely photograph of the building that I work in on a particularly sunny day. And to be fair, it's not too bad today looking out the window. So a little bit of a background there. So Formulation was founded in 2015 as the Formulation and Flexible Manufacturing Centre. This evolved into the National Formulation Centre in 2018, shortly after I joined. And we're now simply called Formulation because National Formulation Centre was just too much of a mouthful. We're interested in all aspects of formulated products. So you can come to us with a formulation problem and we'll probably have someone that's worked on something similar and can sort of direct you in that. I know for a fact that some of the things I've worked on have been fast-moving consumer goods. We've had batteries, inks, you name it. We can probably figure out how to make it work. This formulation facility is home to around 75 technical team members now. So it's kind of exploded in the last few years from around 20 to 30 people into the facility we have now. and we kind of broke them down into sort of general specific teams, so areas of expertise that are sort of compatible with each other. The next slide, I'll apologize in advance. The eagle-eyed among you might realize that is indeed me in one of the marketing photographs that I managed to find on our shared drive. The moral of the story there is don't walk into a lab if you see someone with a camera, because you'll probably get grabbed. So I started at CPI in September 2017. It was my first real job after leaving university, and the place was a lot smaller then. The facility I'm sitting in now we hadn't actually built it yet. It was a building site. I started in the colloids team for about a year, working on colloids-based projects. Then up in our high throughput informatics and process analytics team, and I moved to there a year later, and I've been there ever since. And what we do is we use a lot of automated systems to sort of make, mix, analyze, draw down, process formulations in a wide variety of ways. So in terms of the capability that we have as a team, so we have a number of automated platforms formulating products. So we've got 2 ChemSpig technology platforms, which are very nice, very powerful formulation systems. We've also got the new sort of LabMan formulation engine that we designed and built with LabMan, sort of filling the gaps that the ChemSpids weren't too good at. So in there we have, that is particularly designed around batteries materials, because the part on the end there is a nanomaterials glove box. So the robot can actually process all kinds of nanomaterials safely in a high throughput manner. And we've had the pleasure of working across all areas of formulation. So we've had, deodorants, we've had washing up liquids, we've had inks and adhesives, we've had batteries materials. You name it, we've probably looked at it and probably figured out a way to make a robot do that. So one of the things that you kind of learn from working with these automated systems is they all have their own quirks and they all have their own sort of software behind them. And I think that was probably the reason that got me interested in LabVIEW in the first place, as a kind of way to tie some of the things together if we could. So moving on to a little bit about some of the ways in which we've used LabVIEW here at Formulation. And a lot of it is fairly high level stuff. So I'll talk a bit about the science behind it before I then go on to talk through how we've sort of used LabVIEW within that particular field. So one of the instruments we were quite keen to develop was an inline TFF. So TFF is tangential flow filtration, for those who aren't aware. And essentially it's a way of filtering out large amounts of material by using like a back pressure to filter for solvent small particles through a filter column. So in the example I give here, your material will circle around in a loop, and every time it passes through the filter, something will filter out into the permeate. Typically, this is a batch process running in a loop. So you fill your vessel with whatever you've made, you filter it down, you can then add clean solvent in, and you can sort of wash out material as you go. So it's quite a nice process. It's one we've used quite extensively in the nanopharma industry. So for that, you want to, if you're starting with your materials in ethanol, you can't generally go around injecting ethanol into patients because there are sort of health implications for that. But you can then use TFF to gradually replace the ethanol phase with a biocompatible buffer that you can then work in. So a liquid flow is generated through the use of a pump. Normally we use a peristaltic, but other options are available based on what you want. And you monitor the pressure that builds up in the line through the pressure sensors. So you don't want your pressure getting too high. You could damage your filter, and then everything goes through it. Now, commercially available single pump instruments are available. So a company called Repligen, they do sort of inbuilt flow loop TFF systems, a variety of scales and sizes. It's a really nice technique because it really scales quite well. But one of the problems we had is that because it's a batch process, you need to finish your entire experiment before you try and collect your product. So we wanted to look and see if it was possible to collect the material that comes through the filter and then pass it on to maybe a second, third filter. So the system we developed was an inline TFF where you have 3 filters arranged in sequence. So 1 leads to 2 leads to 3. This needs 3 pressure sensors at each filter. So you need 1 for the inlet line, 1 for the outlet line, and 1 for the permeated material line. For each one of those, you need 2 pumps for each filter. So you've got one to actually feed the material in, the second to feed in your wash solvent. And so you've got, you know, nine pressure sensors, you've got 6 peristaltic pumps. We needed a common control interface for that. So the solution was we used LabVIEW to basically pull our instruments together into a common interface, because you don't want to be, you know, individually controlling each and every pump and worrying about getting the flow rates right. So the interface that we built, which I'm sorry, I can't show you because my LabVIEW version isn't up to date at the moment, so I don't actually have that ability on this new laptop. But we can control the flow rates from each pump, so we can independently change what each pump is doing. So we can, depending on the flow rates that we have the solvent mixing at a different ratio. It also receives feedback from the pressure sensors. So there's an emergency stop built in the LabVIEW code, where if one of those pressure sensors gets to a particular point, it will shut the whole system down in order to prevent damage to the filter. So it's a fairly basic sort of interface that we put together, but it works quite nicely in terms of being able to run an independent piece of equipment in a controlled manner. The next thing that we went on and sort of have used LabVIEW for has kind of been something similar, but in a more sort of condensed package. So this is what we call MicroSTAR, which is the microfluidic stability rig, and this is something we've developed with Imperial College and P&G. So I am allowed to talk about this because we do own the IP rights to this one. But for the sake of industry standard testing, you tend to test stability of a sample, you will have a bottle of it, you will put it in the oven for a week to a month. You'll then take it out, you'll either leave it on the bench or you'll put it in a fridge, again, for a week to a month to make sure the whole sample, could be a litre, has actually reached that temperature. Pass it backwards and forwards between those temperature ranges and check it to see if you're seeing crystallization or precipitation or something falling out. So obviously this process takes months to complete and is quite a problem if you're trying to really turn around new formulations quickly. So a lot of the time, the big companies, they tend to stick to what they know because they know it'll work and they know it'll give them the results they want. With MicroSTAR, we kind of designed a system where you can take a tiny sample size. So the particular system setup that we have, it doesn't use a mil of material. The temperature cycling happens in a microfluidic chip with about, you can vary the retention time at each temperature from 10 minutes up to an hour. And the experiment at sort of 10 minutes at each temperature range takes about an hour to complete. So you get the same results in a fraction of the time. So how does it work? Well, the image on the right there shows you sort of how it actually looks. So we've got a microfluidic chip there with a serpentine path leading through it. This goes across 2 temperature plates, and we can independently set those temperatures to whatever we want. So we can replicate whatever industry test we have. The liquid comes in one end, passes through the chip, and then comes back out the other. So because you're dealing with such a small volume and it's traveling reasonably quickly through a small area, you get really rapid heating and cooling. So the evidence that we have suggests that the temperature change from, say, 0 to 40 degrees is instantaneous. You've got a very low volume, high interfacial area, so there's no problem in actually getting the material to temperature. You can go at low flow rates, so the limit there is how slow can you pump the liquid through it. So you can actually have it spending time at each temperature, even though it's a few millimeters of pipe. This has been found to be really good at sort of probing failure modes by a thermodynamic equilibrium. So if something's crystallizing or something's precipitating or your mixture is just failing in some way that is thermally reproducible, they become more visible the further down the sample, but down the chip the sample goes. So the example on the right, the first sort of cold loop, the sample's been in that chip about 10 minutes by that point, and you can see something sort of vaguely in there, but by the time you get to the 4th loop and it's been in there close to an hour and a half, you can see there's quite a significant failure going on there, and that is not recoverable at a particular time. So again, what we've used LabVIEW for is essentially to take the instrument in its various components. So we've got 2 temperature controlled Peltier plates, a syringe pump for sample flow. Actually, we just upgraded to a new syringe pump that has sort of 2 chambers, so we can mix in the chip as well. We've got a microfluidic pressure and a flow rate sensor, so we can actually get feedback to make sure what the pump thinks it's doing, it's actually doing. And a nice high-performance digital microscope with an X-ray stage, so we can image any part of the chip that we want to look at. The future plans, we're in the process of buying a TCAN Omni, so an auto sampler. So we'll be able to sort of have a well plate of samples and just have the system load each of those samples in and take images all day long. So where LabVIEW comes in here is, again, we've been using it to sort of integrate these components into a common interface, so we can control the temperature at the stages and record over a given period of time how the temperature's changed. So if there is a variance, what is the variance? We can record the flow rate or the target force from the pump, which is generally as important. So if you want the pump to give a particular force, so you can measure viscosity by knowing a given force behind the pump, you can do that. Feedback recording from the flow and the pressure sensors. So at the moment, it's basically just producing a graph of what the flow is and what the pressure is. But potentially, I would like to be able to then create a feedback to that, so that if the pressure starts to go up, it can slow the flow rate down in order to give you that balance and control there. Potentially, we'd like to integrate the microscope, so we can actually program it to move to particular areas when there's a sample in there and take images for us. And of course, we've got the sample loading, tracking and recovery via the auto sampler. So the plan will be the auto sampler will inject it into the chip, it'll pass through the chip, it'll then come out and be collected into a second well plate. So you could then take that and do further analysis on it after it's been inside the chip. Things that I'm quite keen to do that I see LabVIEW being potentially useful for in the future is we could use it for data capturing. So, I mean, really any device that generates a flow of data, you could potentially use LabVIEW to just capture and generate a graph of that. So one of the examples I've given is monitoring mass change over time with a balance. Can you believe it or not, one experiment that we used to actually do around here was to record the change in mass of a particular reaction by setting up a camera and taking images every 10 minutes and then spending time looking through those images and typing out the number that the balance is spitting out. So pretty much every balance you get nowadays has a serial connector on the back, link that into a PC, put a script together in LabVIEW, suddenly you've got something that can spit out a graph for you or a CSV, whatever data output you want. Again, similarly, recording temperature changes. So if you've got a thermocouple that you can attach to your formulation, you can then measure the temperature of that reaction over time. If the temperature starts to go up, you can reduce the temperature externally or add some other methods of sort of slowing down your reaction rate. The second option, which kind of feeds into that, is the sort of tying it into some process analytics. So we already have a few instruments that have their own PAT tools. The idea of a PAT tool is that these are supposed to these monitor what the process is doing at all times in real time, and then by training them with what to do in a particular instance, they can then automatically adjust themselves in order to keep the process within a certain set of conditions. So what I see us being able to potentially do is tie LabVIEW into something doing a simpler task. So anywhere where we have a process where we want control over it, we could potentially build something in LabVIEW to monitor that from all the feedback from the sensors. Like I was saying with the MicroSTAR example earlier, if you have the feedback of data coming in, you could then have LabVIEW say, if this is too high, do this to adjust it. I'm not suggesting LabVIEW is advanced enough to be able to really do the machine learning part. I was quite interested to hear about Lewis's particular examples in Python there because we do have some Python experts around. So there's some potential we could sort of integrate that in, and that gives me a few more opportunities there to really think about what we could do there just to make our lives easier so that we don't have to have somebody standing there with a camera taking pictures and changing a process sort of manually. So I guess to summarize, we can use LabVIEW to assist in some of the formulation preparation and the analysis techniques that we have. Currently, we've been using it as a control interface for sort of in-house built instrumentation, but I'm quite keen to explore what other opportunities we can get out of LabVIEW, bearing in mind I'm a chemist. I have zero experience in programming before starting with the LabVIEW training, so I'm quite happy to be sort of find out as I go. I would like to see us using it more in data capture or process analytics, so quite keen to see if I can drive that forward internally. And heck, I'm open to further suggestions. So if anyone has anything that they think might be of benefit to us that they know LabVIEW can do, or if you have any questions that you would like to ask me, please go ahead. Thank you for listening.
Cheers, Adam. That was really good. Nice to sort of hear about what you're up to there. I got a couple of questions. How did you find the kind of learning experience, and where did you go for? Have you done the training courses, or have you sort of self-taught? Oh, you're muted, Adam.
What happened there? Somebody wanted to shut me up. Yeah, we do have a couple of people who have done the training course in the past. So we had the course notes around from the core 1 and core 2.
Yeah.
So when the sort of pandemic kicked off last year and we're all stuck at home for a while, I was able to take these home with all the software and kind of work through them myself.
Yeah.
So mostly self-taught, and a lot of the code that I've looked at has been sort of pieced together from what other people have done.
Right. Yeah. And have you developed any of the code you talked about in that presentation?
Yes, I was the one who figured out how to include the emergency stop for the TFF.
Oh, nice.
So being able to put a hard limit on the pressure is probably the most important part of that particular interface. And I'm the one who's actually working on the MicroSTAR code now. So
nice. And what sort of architecture are you using there? Have you gone for a particular framework, or have you sort of done your own?
Yeah, to be honest, I've just been looking at other examples that people have used and sort of basing it off that rather than trying to reinvent the wheel. So there was quite a bit of, in terms of MicroSTAR, there was quite a bit of prototype work done at Imperial College. So the guys down there had managed to put together some code for like the heating plate because they have the same heating stage as us. So I've kind of taken that as a starting point, and I'm building in the extra components that we have.
Yeah, because it's nice to hear. Well, nice to hear different people's experiences of becoming sort of proficient in LabVIEW, isn't it? Because there's lots of different ways you can go about doing it, and lots of different frameworks and architectures that are out there that people recommend and all that kind of stuff. There's quite a lot to learn.
There is.
Sometimes it's just good to get stuck into it.
Yeah, absolutely.